Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So we meet here again now for the next lecture, Statistical Process Control. For this lecture, we're going to look at SPC and its tools for a start. Then we're going to look at variation reduction as quality monitoring approach. I'm going to describe some quality characteristic. We'll also be looking at the two types of cause of variation, which are chance and assignable variation. And going to look at control chart itself, the properties, and two phases of control chart. Now, statistical process control is a powerful collection of problem-solving tools which is very useful in achieving process stability through reduction of variability. Yeah. It is a methodology for monitoring a process by identifying special cause of variation and the signals so that corrective measures, corrective action can be taken when appropriate. Yeah. Now, there are 7 basic tools under SPC. Yeah, we have histogram, stem and leaf plot, or sometimes you call it box and whiskers plot. Check sheet, Pareto chart, cause and effect diagram, defect concentration diagram, scatter diagram, and control chart. Okay. As you all know, the main part of this course is SPC, specifically for control chart. Yeah, histogram and stem leaf plot. You are familiar with these two tools. Yeah. Check sheet. This is actually a diagram from the shop floor itself, or rather from the factory itself. Pareto chart, cause and effect diagram, or sometimes we call it Ishikawa diagram or fish and bone diagram. Defect concentration diagram, this is more towards very technical. No, we are not going to do this. Scatter diagram, you already know what scatter diagram is, or rather sometimes we call it scatter plot. Yeah, and then control chart itself. Now, going back to statistical process control or SPC, we all know that all activities in industry produce items, products, services, which are subject to variability or variation. Yeah? The word that we used in the previous lecture is that variation is omnibus or omnipresent. Yeah? It's always there. So product or services should be produced by a stable process, which is a process operating with little variability around the target dimension of product quality characteristic. So the key word here is, in order for product or services to be of good quality, they should be produced by a stable process. So a stable process is basically a process which are operating with the minimum variation around mean target, around nominal value. Yeah. So normally target here is the mean value, yeah, of the product, of the quality characteristics to be produced. Yeah. So when we talk about any dimension or any measurement, it is the measurement of quality characteristics. Now, how do you describe quality characteristic? Quality characteristic are the measurable features which describe the quality of product or services. In general, quality is described by variation in the measured quality characteristic. So if you were to monitor the quality of your product, you should be able to identify what are the quality characteristics, and also you must ensure this quality characteristic should be able to be you should be able to measure this characteristic. Yeah. So quality characteristic should be the measurable features of the product or services. What are the example? Some of the example would be conformity, timeliness, accuracy, yeah, completeness, relevant, accessibility, uniqueness. Yeah. So all these, in some cases, they are not straightforward, yeah, to be measured. But in most cases, if you talk about items which produced by a production line, we are looking at the product dimensional measurements. Yeah, that is a very straightforward example. Yeah, on how you can measure the quality characteristic, which is the easiest example would be the dimensional measurement of the finished item or finished product. Now, in many cases, quality characteristics are evaluated in relation to the specification. So, specifications are actually the measurements given by the design department or R&D department. Yeah. So when they have this items to be produced, it comes together with its specifications. Yeah. And for all specification, generally they have their lower and upper specification limit. Okay, coming back again, quality characteristics are evaluated relative to its specification. So normally for product specification, we have three limits, yeah, three values. The first one would be the lower specification limit, and we have upper specification limit, and the target or nominal values. Yeah, so normally these target values the mean values. Yeah. Now, this is a histogram. All of us are really familiar with what histogram is like. So normally for in describing quality characteristic, we can also use histogram. Yeah. So basically, by coming up with a histogram, we can know what sort of distribution of the data set for your quality characteristic. And this is another example where you have different types of normal distributions. Yeah, not only in terms of different values of different mean values for each normal distribution, but also you see some normal distribution will have a different dispersion. Yeah, some would have much narrower, some would be more scattered away. Yeah, more wider normal distribution. Okay, so these are basically the same set of data, but for different months. Yeah, as shown here. So if you were to look at a histogram and its value of lower and also upper specification limit, normally lower and upper specification limits the values which lies above and also below the mean values. Yeah, for a normal distribution, you're going to have mean value which lies in the middle of your normal distribution, and for a normal distribution also you will see that the value of mean is also very much similar to the value of mode and also median. Yeah. So these are the lower, upper specification limit, and the target or nominal values is actually the mean value. Okay. Now, if you remember during those days when you were doing statistics, yeah, basic statistic, you must have come across this confidence interval. Yeah, I also have this link on which you can have a look at. This is from the internet. Yeah, the basic or the foundation of confidence interval. Okay, so if you sort of need some revision on a confidence interval, this will be a quick link to um, the topic of confidence interval. Yeah. So in confidence interval, you have looked at how you have used central limit theorem in explaining the distribution of your data distribution. Yeah. So in central limit theorem, you have three different statements. Yeah. The first statement would say that 68.26% of your total observations will lie in between plus minus one standard deviation, yeah, of the mean values. Yeah? And 95.46% of total observation will lies within 2 standard deviation, and finally 99.73% of your total observation will lies within 3 standard deviation of the mean value. Yeah, so it's very good for you to have a look back at your set of notes on central limit theorem. Okay, so in order to study how control chart behave, it is necessary to relate it to some distribution. Yeah, so the obvious choice will be normal distribution. Yeah, because it has been commonly used and it has given a very satisfactory model. Yeah, and you can whereby you can utilize. Yeah, you can optimize the use of the central limit theorem. Yeah, in explaining the distribution of quality characteristic. Yeah? So this is one reference where you can have a look if in your free time on normality and the process behavior chart. Yeah, this is an article in Journal of Quality Technology. Yeah, it was published in year 2000. Yeah. So if you have time, you can look into the from your library. Yeah, from library, library, we have this the online version of this particular set of notes. So the particular article. Okay. Now, just now we have looked at histogram. Yeah, histogram basically tells you the distribution of your data set. Yeah, if it is normally or not normally distributed. Yeah? And we have also talked about control chart very briefly on how control chart can actually can give you more information. Yeah, on the distribution of your quality characteristic data. Yeah. There are a few points which make control chart a better quality control tools, yeah? Better SPC tools in comparison to histogram. Yeah. The first one is histogram do not take into account changes over time. Yeah? So it does not have, it is not established or it was not developed based on time period. Yeah. So control chart, yes, you will see the sequence of time and when exactly does those quality data set occurs. Yeah. General. Yeah. So this is an histogram, and from histogram, obviously you can see that the data is normally distributed with its upper and lower specification limit. Yeah. Now, so again, in histogram, what you will see is these points of data being represented based on its x variable and the frequency for each and every x variable. Yeah. But what does a control chart can tell you is when the process changes. Yeah. Histogram only tells you the distribution of the quality characteristic. But control chart have one more dimension, which is time dimension, which is not available from a histogram. So with the same set of data, you can use the same set of data, but you can come up with a control chart. So a histogram may conceal significant in the sequence of measurement, meaning to say that you wouldn't know when exactly this particular data set or which particular quality values occur. But in histogram, you will easily detect. Okay, this particular quality characteristic was measured at time 1. The next one is measured at time 2, so on and so forth. So you will see the reading of your quality characteristic, whether it is going up or down, and when exactly does this reading were made, or were collected or were recorded. Okay, this is another example how you can track the data set, which was drawn or which was plotted in a histogram, in a form of a histogram. But by using a control chart, you can easily see whether those values are above or is below the nominal values. And in particular, you will identify if the particular value lies below the lower or the above the upper specification limit. Even if you can also detect that from a histogram, you wouldn't know exactly when does this out of control occur, because it does not have the time. It was not drawn based on a on time basis. But for control chart, we will see exactly when does it occur. At this point of time, the out of control have occurred, as shown by the red point. Red dot. Therefore, variations represented by control chart can be better analyzed. So you can see whether the data, not only the positioning of these points, exactly when it occurs at which point of time, but you can also detect the variation from one point to another. Okay, so a bit of question here, why again, the answer will be still be the same, because you can exactly identify when does those variation occur. So that is the beauty of control charts in comparison to histograms. So we have looked at earlier on how do we define quality improvement. Quality improvement, or rather Deming has come up with a definition for quality improvement, which is reduce variation and then you can improve quality, because quality is inversely related to a variation. So if you want to increase quality, you have to reduce variation. So similarly here, control chart, the basis of control chart in controlling the quality of a process is based on the variation study. So under control chart, what it can tells you is that it will let you know whether your process is in a state of statistical control or not. So it will help you to establish exactly what is the state of statistical control for your process. And with this definition of state of statistical control based on the process, you can monitor the process and a control chart will help you to give the signal whenever the process has go out of control. Yeah. And then from a control chart also you can determine the process capability. Yeah, it's very important to differentiate the difference between process stability and process capability. Yeah? What you can observe from a control chart is process stability. Yeah? By using some information from your control chart, it can also help you to determine the process capability, yeah? Whether the process is capable or not. Okay? So a process is considered to be in a state of statistical control if variations among observed sampling result from it can be attributed to a constant system of chance causes. Yeah. So when you talk about a state of statistical control for a process, you will relate that to the variation which is caused by chance cause only. Yeah. So when there is the presence of chance causes variation in your process, so the process is said to be in the state of statistical control. Yeah. So this definition has been given out by the ASQC in 1987. Yeah. Later on, you will see that there are two types of variation. Yeah, we talk about chance variation just now. There'll be another type of variation, which is assignable cause of variation. Yeah. So for a process to be in a state of statistical control, there is only the presence of chance variation in the process. Now let's have a look at how control chart can tells you whether your process is in the state of statistical control. Yeah. So in general, a control chart contains a center line, the upper control limit, and the lower control limit. Yeah. If you remember, just now we have looked at the specification limits. Yeah. We have upper specification limit, we have lower specification limit, and we also have the center line, yeah, which is normally equals to the target or nominal values, yeah, and similarly in this case it will be the mean value. Okay, so this is what your control chart would generally looks like. Yeah, you have the variables, yeah, the quality measurements reading on the vertical axis or y-axis, and on the horizontal is actually the time sequence, yeah, exactly when those quality readings occur. Yeah. So in general, what you have is what you're going to have are points, yeah, points of quality readings, yeah, which you measured from your product. But normally in a control chart, you will join all these points. Yeah? So you'll see these like lines on your control chart. Yeah. So again, your control chart, you're going to have upper control limit, lower control limit, and the average value will be in the middle. So a point that plots within the control limits actually indicate that the process is in control. So for example, at this particular point of time, your process or your quality reading is at this level, and this point at this level, it is within the lower and upper control limit. Yeah, it's within these two limits. So at this particular point of time, you say that the process is in control. Yeah. Similarly, if any point at all which lie within the two limits, those times are the point of time whereby the process is in statistical control. Yeah. So by using a control chart, you can say that the process is in statistical control when the process value, or rather the quality characteristic values, lies or located within the two lower and upper control limits. Yeah. Now, if there's any case whereby a point plots outside or beyond the two limits, this is an evidence that the process is out of control. Yeah. So this is an example where you will see this particular point. Yeah, this particular point actually lies above the upper control limit. Yeah. So if this happens, you know, at this point of time, at this point of time, the process is not in statistical control or out of statistical control. And when that happens, what you're going to do is you're going to perform some investigation to find out why at this point of time the process value or the quality readings at this point of time is actually above the upper control limit. Yeah. So when you know what are the reason, you should be able to discuss with the shop floor workers or anybody who are in charge for the corrective action to be taken. Yeah. So any problem should be rectified, yeah, at this point of time. So you need to find out. Yeah. So in some cases, at this point of time, there's a power trip, yeah, or even the operator are not of good or of low skill worker at in charge at this point of time. So there occur some problem. Yeah. Right. So if you look at this condition whereby we can say whether a process is in statistical control or not in statistical control by looking at the position of those points. Yeah, if they are within the two limits, then the process is in statistical control. Otherwise, we say that the process is not in statistical control. So what you can say is there is actually a connection, a close connection between control chart and hypothesis testing. Yeah. So I do hope you still remember what is hypothesis testing. Yeah. We're going to look at that again later on the part on hypothesis testing. Now, here, let us look at two types of variation which will cause problem to the process. Yeah. So the two types of variation, or we say cause of variation, cause of process variation, can be seen in terms of chance causes or assignable causes. Yeah. So if a process is operating with only chance cause of variation, then the process is said to be in statistical control, and the process is still a stable process. Yeah. However, if there's a presence of assignable cause of variation, then the situation is the process is out of control. Yeah. So whenever a process is been identified as process which is out of control, on which the point of process value lies beyond the two limits, then we say that there's actually present of assignable causes. Yeah. So the out of control condition which occur in the process is due to the assignable causes of variation. Okay. So again, this is the situation of stable process which is in statistical control, whereby all points are distributed within the control limit, and if there's any variation which occurs in the process, it is only due to chance cause of variation. Chance cause of variation. On the other hand, if there is presence of assignable cause of variation that will lead to some points distributed outside the control limit, and therefore the process is said to be out of control and it is no longer stable. Yeah. So in this diagram, yeah, this diagram is actually from Montgomery. Yeah? If you have read Montgomery, you will come across figure 5.1. Yeah? The later version, this topic will goes into chapter 6. Yeah? Okay, now from this diagram, you will see there are three dimensions. Yeah, three dimensions of graph. This is a three-dimensional graph. Yeah, where on the x-axis actually the reading. Yeah, the reading of the quality characteristic. Yeah, where you see the lower specification limit, upper specification limit, and mean, which is in the middle. Yeah. So therefore, the vertical axis will be the frequency. Yeah, the frequency, or how many times does those readings occur? Yeah, the quality readings occur at those point of time. And also you will notice that on the third dimension, it represents time. Yeah, the time period. Yeah, time sequence. So what you'll see here is the first distribution of data set, quality characteristic, yeah, on which the distribution of quality characteristic, yeah, this data set. So at this point of time, you have a set of data, a set of quality characteristic data, whereby the distribution is shown here, and then the mean of this distribution lies exactly on the process mean. Yeah, exactly on the process mean as being specified. Yeah, earlier on, which come together with the value of lower and upper specification limit. And you will see that the dispersion, yeah, the dispersion of this data set is as such. The data is all distributed within upper and lower specification limit. Yeah. For the second distribution, it is also basically the same. Yeah, where you will find that the mean value for this sample set of data, yeah, at this point is also equals to the process mean value, and all the data are distributed within the two lower and upper specification limit. Okay. Similarly, goes for the third data distribution. Yeah. But if you were to look at more carefully, the shape are slightly different from one to another. Yeah. So you have four points of data on which at each point of time there will be a set of data shown by the data distribution here. Yeah. But if you look at the next two set of data, especially the fifth data set, the mean value of this sample actually lies on the upper specification limit. Yeah, and due to that, you will see some of the quality that readings goes beyond the upper specification limit. Yeah, or lies above the upper specification limit. Yeah, so similarly, that goes to the next data distribution. Yeah, on which the mean value lies exactly on the upper specification limit. Okay. So because of that, we are saying that um, at this for these two data distribution, assignable cost is present, yeah, and as such, the process is said to be out of control. So for the two uh, these two data distribution, it clearly shows that there are present of assignable causes which has made some points lies above the upper specification limit. Yeah, some points lies above the upper specification limit. Okay. And for the next data distribution, what you'll see is the sample mean also lies exactly on the process mean, mu naught. Yeah. However, the data is more dispersed, yeah, as such that there'll be some points which goes lower than the lower specification limit, and some will go above beyond the upper specification limit. Yeah, so you're saying that for this data set, it is more dispersed. Yeah, as such that the sample standard deviation is larger than the process standard deviation. Yeah. For the earlier data set, yeah, especially the first four set of data distribution, the sample standard deviation are very much the same with the process standard deviation, yeah, with the population standard deviation sigma naught. Yeah. So what happened here again? It will be a situation of out of control. The process is out of control because there is a presence of assignable causes. Yeah. So the first set of assignable costs occur during the fifth and the sixth data set, yeah, at these 2 points. But the following data set, which is on the seventh point time sequence, there's also the occurrence of assignable causes. As such, you will see some points lie below or located below the readings is below the lower specification limit, and some would go beyond the upper specification limit. Yeah. Similarly, if you look at the last set of data distribution, you will observe that the sample mean value lies exactly on the lower specification limit. Yeah, and also the dispersion of data is more varied, is higher. Yeah, it has a higher dispersion. As such, the sample standard deviation is actually larger than the process standard deviation. So again, we are saying that there's a presence of assignable causes which has led to the process to be out of statistical control. Yeah. So again, this is exactly the same what we have looked at just now. For each of these point, yeah, these are actually the reading of a set of a sample, yeah, of a sample. We have a sample of a sample comprised of several observations. Yeah, at each point we have a sample of several or a number of observations. Yeah, so and from here also we can identify a situation of out of statistical control. Yeah, because there's a point which lies above the upper control limit. Yeah. So again, the central value of your control chart is actually the mean value. This is an example of how you can compute the upper and lower control limits. Yeah. So this is a heartbreak example of heartbreak production. Yeah. So to assist in understanding the statistical basis of control chart, we now consider how control limits were determined. So in this example, the process mean is equal to 1.5 microns and the process standard deviation equals to sigma 0.15 microns. Yeah. So we also know that the sample size of n equals to 5 are taken. And with the sample size n equals to 5, the standard deviation of the sample average is given by this formula. So this formula is actually the formula of standard error. Yeah. So if you see the situation here whereby you are selecting different samples, yeah, from the population distribution. So this is actually the concept of sampling distribution. Yeah. So for a sampling distribution, you'll know that the sample standard deviation is actually equals to the standard error. Yeah, the formula is equals to population standard deviation divided by square root of n. So this is your n here, which is equals to 5. Yeah, so you have computed here the standard error. Therefore, if the process is in control with mean flow width of 1.5 micron, then by using central limit theorem, we can assume that S bar is also approximately normally distributed, and therefore the percentage, yes, certain percentage, which is 100 times 1 minus alpha. So alpha is the level of significance. Percent of the sample mean X bar will fall in between 1.5 plus Z score times standard error, and on the other limit will be 1.5 minus, yeah, your Z score for alpha divided by 2 times the standard error. Yeah, remember you are dealing with two limits. Yeah, you have upper and lower limits. So your standard your level of significance alpha will be divided by 2. Yeah, so I do hope you clear on all this. Yeah, on which it is the application of normal distribution as well as sampling distribution. So we can arbitrarily choose a constant for z which is equals to 3. Yeah? So this is a normal practice, yeah, rather than we use exactly value of z based on probability alpha divided by 2. We're going to take this constant z score to be equals to 3. Yeah? So the upper and lower control limit can be computed based on these two formulas. Yeah? Which is upper control limit equals to the mean plus 3 standard error. Yeah? And the corresponding lower control limit will be 1.5 minus. Yeah, lower, therefore you minus 3 times your standard error. Yeah, so the simple computation would be UCL upper and control limit can be computed based on mean plus minus 3 times standard error. Yeah, and then you have the value of upper and lower control limit as shown in the control chart. Yeah, so typically control chart will have a 3 sigma control limits. Okay, as we have looked at just now, this value 3. Instead of using more accurate value 2 point something, we take only 3 as the computation for 3 sigma control limits. Yeah. So again, this is the knowledge of confidence interval central limit theorem. Yeah. So by right, the upper and lower control limit is actually based on the third statement of your empirical rule, yeah, which states that 99.7% of total observations will lie within plus minus 3 standard deviation of the population mean. So I do hope you get this correct. Now, going back to the heartbreak example, yeah, it is very important to identify the what exactly the quality variables, yeah, the quality characteristic. What is the variable? How it's being measured, and exactly if also if you have the units, yeah, that used to measure that particular quality characteristic, yeah. So it will give you the data set, which will give you the data set. So the process can be monitored by the average flow width, which is actually the quality characteristic of heartbreak. We know that the sample size is 5. Process mean is 1.5 micron. Process standard deviation is sigma equals to 0.15 microns. Yeah? So these two values actually belong to the population, to the process values. They are process values. Yeah? So note that in this example, all points that falls inside the control limit, so that you will conclude that the process is said to be in statistical control. Yeah. So there you have the upper and the lower control limits and all the points. Yeah. Originally these are points. So these are the points, and later on you join all these points to come up with the control chart. So for a control chart, you're going to see lines, or rather the jagged lines, yeah, which represent the reading of your quality characteristic. Yeah. So for this heartbreak example, the data point that is being given will show that the process is actually in statistical control for the set of data. Yeah. Now coming back to hypothesis test. Yeah. So we have said just now there is a close connection between control charts and hypothesis testing. Yeah? So a statistical hypothesis is a statement about the value of parameter from a probability distribution. Yeah? So for example, in the application of control chart, what we like to know is we like to know if the mean is in statistical control or not. Yeah. So the test hypothesis will be on the mean, and I'm going to say that the process is in control is mean. The sample mean is equals to the process mean or the population mean, which is mu naught. In the test of hypothesis testing, we're going to use a sample data from the process to see if the mean of this sample is also equals to the process mean. Yeah? So we will write as such null hypothesis mu equals to mu naught. Yeah? So when this happens, process is said to be in statistical control. Against the alternative hypothesis whereby mu not equals to mu not equals to the mu naught. The mean of your sample does not equals to the population mean. Therefore, if that's the case, then the process will be out of control. Yeah, so that's your hypothesis statement for null as well as alternative hypothesis. Next is for you to take a random sample from the process. You collect data, sample data, and then you will compute the appropriate test statistic. Yeah. So from the sample data, you will obtain the value of x bar, and you can also compute the sample standard error. Yeah, the standard error for the sample. Okay. So here we have we're gonna use the Z statistic, yeah, to come up with the test statistic for this hypothesis testing. And I'm sure you're quite familiar with this formula of transforming X into Z, whereby it is actually the sample mean minus process mean or population mean divided by standard error. Yeah, and the computation of standard error also make use of the population standard deviation. Okay. So next step is for you to pick the level of significance denoted by alpha. So it is also known as the type 1 error. Yeah, and you need to find the critical value based on your Z as well as your selected level of significance. Okay, this is the normal stage of conducting hypothesis testing. Yeah, I'm sure you are also familiar with all this. Yeah. Next is for you to reject your null hypothesis based on the base of the value of your standard your test statistic. Yeah, is it larger or is it smaller depending on your null hypothesis and also your level of significance alpha. Yeah, because those will determine your criteria for you to reject or not to reject the null hypothesis. So this is the diagram. Yeah, you're gonna see in a normal distribution, you're gonna have lower and upper tail, whereby this lower and upper tail is exactly equals to the level of significance divided by 2 on each side. Yeah, and from here you can also identify the value of negative Z and positive Z. Now, if you were to look at your null hypothesis, yeah, you will come up with a conclusion based on your computed Z and also the critical Z. Yeah, so what you have computed from your formula, this will be the computed test statistic. Yeah, and that will be compared to the Z that you read from table. Yeah, so this is the criteria. Yeah, so if you find out that your X bar, your sample mean value is larger than value of mean plus Z score times standard error, yeah, which is actually uh, Z X bar larger than the upper control limit. Yeah. So if this is the case, then you're gonna reject the null hypothesis. Similarly, if any value of Z, yeah, Z statistic which you have computed is larger than the given value of X, yeah, then we're gonna reject the null hypothesis because the sample mean is smaller than the lower control limit. Yeah, meaning to say that the value lies below the lower control limit. In this situation, the point which is larger than this control limit, obviously it will lies above the upper control limit. Yeah, so for these situations, you're gonna reject the null hypothesis. Okay? And you're going to come up with conclusion saying that the process is not in statistical control. Okay, so based on what we have done just now, we can look at here how we can derive the upper and lower control limit for Short control chart. Yeah, Short control charts for you will see that the computation of upper and lower lower and upper control limit is exactly the same with the computation that we have looked at just now, whereby for each control limit, you're going to take mu plus minus k standard error. Yeah, so in this case is L. Yeah, so L is actually the constant that you use in order to. Okay, if you look at how short control chart works, yeah, we did explain just now where for each and every point that we have on the control chart, yeah, these are actually value of sample means. Yeah, these are also value of sample means. These are sample mean values because at each point you select a sample and you computed the mean values. Yeah, so what you plot on this chart are actually the mean values. Yeah? So in actual fact, this is the application of those of sampling distribution. Yeah. So originally, if you were only to apply individual set of data, yeah, individual data without having to select sample data, a group of sample observation at each point of time here, you are applying the distribution of you are looking at the distribution of individual measurements. Yeah, although they are normal, but most likely it will show you a situation of out of control. But um, what would be a better approach, which has been introduced under Sure control chart, is the application whereby you use sample mean values. Yeah, you use sample mean values rather than the individual values. Yeah, so by using the sampling distribution approach, yeah, what you get is the distribution of sample means, and the normal value will also be exactly the same, but the dispersion, the standard error, which is will be much reduced, yeah, compared to the standard deviation of the individual data. Yeah. So the application of standard deviation, or rather the use of subgroup mean, the value of sample means for each point of the process will actually give a better situation where the process will be in statistical control. Yeah, it will shows that the process is in statistical control. Okay. So when a process is in statistical control, the points on the control chart will fluctuate randomly between the two control limits. Yeah, and if you say fluctuate randomly, you should not be able to identify any pattern. Yeah, so the fluctuation of points within the two control limits should be of no recognizable pattern. Yeah. So if that's the case, then again, we know that the process is in statistical control. Okay. So when are the situation whereby the process is said to be out of statistical control? Number one is when you identify some points actually lies outside the control limits. When there is a sudden shift in process average, yeah, the process value, mean value, there's some changes in those average values. There are cycles that you can identify from the control limit. You can identify trends, yeah, of the points, although they are within the control limits, but you can identify some trends of points. Yeah. This also situation whereby all the points are lies very close to the center line. Yeah, so this is a situation of hugging the center line. Next, it hugging the control limits. Yeah, those points are really close to either one of the control limits. In stability, yeah, or rather the variation is huge. Yeah? When variation is huge, then you say it's a unstable condition. Yeah. This is the illustration whereby in the control chart, upper and control limit, you will see situation whereby there's a group of points, yeah, which shows that the sample mean value has actually shifted upwards. Yeah, from the original center line of the process mean, it goes upward. Yeah, so this is actually a shift of the process average. Yeah. So in order to determine this shift, yeah, you can identify whether The shift is actually 2 of 3 above the standard error, or is it below the standard error? So here it shows that two of out of 3 points here is actually above um, the standard error. This one is below the standard error. 1, 2, 3, 4, 5. Yeah. So 1, 2, 3, 4, 4 points actually lies below one standard error. Yeah. And this one 8 points altogether on one side of the center line. Yeah. The center line is here, but a large number, large number of points actually lies above or lies at one side of the center line, either above or below. So this is identify the occurrence or the presence of shift in the mean value. Yeah. This cycle, yeah. This is trend downward, downward points, yeah. Downward quality characteristic readings, yeah. Downward trend. Process stationary can be in terms of process variability, can be in terms of can exist, yeah, can exist in 3 different conditions. The first one is stationary and uncorrelated, yeah. This is stationary, but it is not correlated, yeah, uncorrelated. So data may vary around the fixed mean, yeah. So this is situation whereby it is actually stable, yeah. The process is stable and predictable. Next is the situation or the condition whereby the variation is stationary, but it shows some correlation, autocorrelation. Sorry, some autocorrelation. The presence of autocorrelation. Yeah. So it can be shown by the successive observation, which are dependent with the tendency to move in long runs on either side of the mean. Yeah. So you can see a persistent trend of points, yeah, which is due to the presence of autocorrelation. Yeah, so if you have done applied econometrics, you have gone through the topic of autocorrelation. Yeah, how do you actually identify the presence of autocorrelation? Yeah. We're also going to look at one particular type of control chart which will deals with this problem. Yeah. So if you have a problem of autocorrelation, yeah, the answer would be to use a time-weighted control chart, which is called exponentially weighted average, moving average control chart, EWMA, EWMA, you call it EWMA, EWMA control chart. Yeah, so that control chart is specifically for a data which has a problem of autocorrelation. Yeah. Next is the condition of a non-stationary. Yeah, non-stationary meaning you cannot identify the stability. Yeah, it keep on changing. Yeah, the process drift, but without any sense of stable or fixed mean. It keep on changing. Yeah, so this is a situation or condition of non-stationary process variability. Okay. So why control charts are so popular for process control? Number one, control charts are proven technique to help in improving, yeah, productivity. It will not help to improve productivity. Sorry, it is not a direct approach, yeah, but it will help you to identify problem. Hence, you will rectify. Therefore, you will further improve the productivity. Okay. Next, the control chart are effective in defect identification, hence prevention. So when you can identify the defects, yeah, the presence of any defects, then effectively you can do some rectification, and you can prevent, yeah, such occurrence in the future. Control chart prevent unnecessary process adjustment. So if you don't get any signal, from control chart, meaning there's nothing you can do. You don't have to do anything. Just leave it alone. Control chart provide diagnostic information. Diagnostic information here meaning that you can identify exactly when the problem occur. Again, because time control chart take into consideration the time factor. When exactly the quality characteristic variables are being recorded. Control charts enhance information about process capability. So by having looked at the stability of your process, you can further study the process capability. This is very important because these two process stability and process capability are not the same. There are two different things. So in control chart, it tells you process stability. Then you will study the process capability. But later on, we can have a look at this later on. Don't worry. Okay, right. So control charts indicate when to take action and more importantly when to leave the process alone. So you don't have to worry if it does not show you, it does not give any signal, then you leave the process alone. Now there are two types of control charts. In most cases, if you were to design a control chart, you first of all need to know your quality characteristic and how you measure them. So when you measure your quality characteristic, you will be dealing with quality data. So and based on that quality data, you will know what type of control chart that you will come up with. So obviously, if your data actually come from the continuous type of data, then you come up with variable control chart. So this is variable continuous scale of measurement. So in this case, quality characteristic can be described by central tendency and measure of variability. So again, if your quality data is actually falls into the category of continuous data, then you will use the variable control chart. Variable control chart. So some of the example of variable control chart are X bar and R chart, X bar and S chart, chart for individuals. So when you see the word X bar here, it shows that you are using the a sample mean approach. Meaning to say that you're going to select a sample observation at a point of time. Whereas if you're dealing with individuals data, meaning at one point of time, you only have one data set. One data only. So that is called X chart. X bar chart is for data which you collect in samples. Okay. So R chart, S chart is basically two different types of control chart for variation. We're gonna look this into detail later on. Okay. Now, the second type of control chart is attribute control chart. So again, here, if you are measuring your quality characteristic based on attribute data or categorical data, then you have to apply the attribute control chart. So this is what you call non-conforming or conforming control chart. Control chart which deals with the number of conforming or non-conforming items. So again, this is used because your quality characteristic is based on counts, attribute data which come in terms of counts. So there are two types of attribute control chart. Number one is P chart and P chart, or C chart or U chart. So this P and P chart, C and U chart are actually the attribute control chart. It is used because your quality data is actually come from the attribute data, or data in terms of counts. Now, how do you develop a control chart, or rather, how do you establish? How do you come out with a control chart? Number one, you choose measurement, as I tell you just now. what will be your quality characteristic, what will be the measurement. Yeah, in some cases those measurement can be in terms of continuous data, some could be in terms of attribute data. Then you proceed to collect the data. Yeah, how do you collect the data? In some cases, in most cases, should I say, you will apply the systematic sampling. Yeah, systematic sampling. Yeah, so please go back and find out how systematic sampling is performed. Yeah, random sampling, not really. Yeah, in most cases, you'll do the systematic ra- sys- systematic random sampling, not simple random sampling. Yeah, everything could be done in a random. Yeah, but it is systematic random sampling. Okay, because you're dealing with time sequence. Okay, so that will determine how you collect data and the sample size. Yeah, again, sample size can be in terms of samples. Yeah, you collect data, a sample of observation at a point of time, or you only pick, or you only use one individual value for a point of time. Yeah, and the frequency of sampling. Now, frequency of sampling here meaning how frequent do you do your sampling? Yeah, not only in terms of when do you do sampling for each production shift or for which production run, but it is more on for a particular production run. Yeah, when you have a production run, say for example, for one production run, you have 4 hours, yeah, 4 running hours for one production run, 4 hours. So out of that 4 hour interval, how frequent do you make your sampling? Okay, so are you going to divide 4 hours into four intervals? Yeah, so meaning to say you're going to do sampling every hour. Every 1 hour you collect sample, the second hour you collect a second sample, third, so on and so forth. Or are you going to collect a sample every half an hour, or even every 15 minutes? Yeah, so that is actually the frequency of sampling. So we are more interested to know what would be the how many times that you do sampling for a production run. Yeah. Then you set up inertial control chart. Yeah, you're gonna look at this later on. Then when you collect your data, say for example, you have finished with your data collection, you come to the point where you record all this data and you're gonna compute the appropriate statistic. Yeah, in most cases, you're gonna compute mean and standard deviation. Yeah, and you're gonna plot all these values on a chart. So this is what you call control chart. Yeah. Then you will determine trial control limits. Remember, we have a set of formula for us to compute the control limits. Yeah, so this would be the point where you will come up with trial control limits. Yeah, I'm going to speak more of this later on. Yeah, so you remember, you have to compute the center line. Basically, what is the mean value of the quality characteristic for that process, and then you're going to compute the standard deviation, and based on those two statistic, you will further on to compute the upper and lower control limit. Yeah, you will analyze, interpret the result. As such, you will state whether the process is in control or not. Yeah, the situation where you find there are points which are actually out of control, then you will do some elimination. Yeah, and then you recompute. Okay, this will be further explained under the two stage or two phases of control chart. Yeah, and you use as problem solving tool. You continue to collect data and plot the data on the control chart, and you take the corrective action if necessary whenever you find a point which is out of control, exactly when it occurs, and you will start rectify the problem. Okay, now in order to develop control chart, as I mentioned just now, you have to come up with a few decisions first of all. Yeah. So this decision will actually help you in designing your control chart. Yeah. So in other words, your control chart design will be based on two things. Yeah. Rather, it will be based on sampling design, and it will actually based on your control limit, which is alpha. Okay. So under sampling design, we have looked at normally you'll be use systematic random sampling as the basis of sampling, the frequency of sampling, and also sample size. Yeah? So these are the three major things that you have to decide before you come up with a control chart. Yeah, you have to think about the sampling design, basically the basis of sampling, how frequent do you do sampling for a production run, and are you going to select a samples from each at each point of time, or you only consider to use one individual data. Then you have to decide your alpha. If you remember, this alpha will help you to determine your value of Z. Remember, Z score depend on your alpha value, because it will determine your critical Z. Yeah? But for sure, it will be based on Z score equals to 3. Yeah? That is the standard procedure. Yeah. Later on, if you look at multivariate control chart here, and you will see how different alpha will give you different value of control limits. Okay, so you must know the formula of control limits first of all for Sherwood control chart. Yeah, which is mu plus minus 3 times standard deviation. Yeah, so that will be the formula for control limits for Sherwood control chart. So in determining the, we come back to basis of sampling. Yeah. So in determining the method of sampling, samples should be chosen to be as homogeneous as possible, so that each sample reflect the system of common or assignable causes, which will present at that point of time. Yeah. So this means to say that because your main objective is to identify the occurrence or the presence of assignable causes. Yeah. So how do you do your sample, or how do you sample your quality character, your products? You should be able. It should enable you to identify the presence of these causes of variation. May it be common cause, or may it be assignable cause. Yeah. So maybe I have not tell you just now. Common causes is the same with chance causes. Yeah. Assignable causes is sometimes called as special causes. Yeah. Different textbook use different term. Yeah. Some would use common, some would use chance. Yeah. For assignable, some would also use special causes. Okay. Now, so again, if you want to decide on your method of sampling, yeah, your sampling should be done as such. It enables you to identify the presence of assignable causes, especially, yeah, because this is something that you can control, yeah. So as such, your samples should be homogeneous, yeah. Homogeneous meaning to say that you are assuming these samples, observations, operated or being produced under the same operation, the same operation condition. Yeah. So this is what you mean by homogeneous. They are exactly the same, yeah, regardless of which sample observation that you select for your sample. They are actually the same with one another because they are operating under the same condition. That is a very important assumption that you have to come up with. Yeah. So in practical, however, sampling is recommended due to time and cost factor. Yeah, even though we know that as we increase our sample size, we're going to get a better data distribution, which will give you more information because your sample size is large. When it comes to practice, you have to consider the time and cost factor. Yeah, all this will actually determine the profits, the cost that you have to incur in your production. So not only the theoretical bit but also the practical bit of sampling you have to take into consideration, both. So there's a saying here by Albert Einstein. He says that not everything that can be counted counts, and not everything counts can be counted. So even so, you can collect as many data. Sometimes those data is not of importance, of not that importance. In some on the other hand, we're also saying that not everything which is important you can count. You cannot count everything, even though you know they are important. That is something that you have to consider. So this is the idea of theoretical procedures and the practical part of it. Okay, so not everything that can be counted counts, and not everything that counts can be counted. Okay, interesting, isn't it? So you go back and think about it. Now, again, coming back to samples, basis of sampling. So samples should be selected so that assignable causes are present. I mentioned just now, if you were to do sampling, it should enable you to identify the presence of assignable causes. If there's any assignable causes, should be able to identify those problems. So in that cases, chance for differences between group of individual measurement will be maximized, while chance for difference within a group of individuals should be minimized. So for you to be able to identify the presence of assignable causes, you have to ensure that differences between groups, so say for example you collect a set of a set of sample observation at one point of time. So the differences between these groups should be maximized. The difference between these groups should be maximized, while the difference within individuals should be minimized. So you have individuals observations within one group. So any difference of these individual measurements within a group should be minimized. Any difference between individual measurements in a group should be minimized. The difference between groups should be maximized. Only by doing this you can identify the presence of assignable causes in any case it is present. Okay. So data set collected by rational subgrouping will show us variation within group that will reflect common variation only. While any significant variation between groups are actually the assignable causes. So again, what we're saying here is if there's any difference between individual measurements within a group, within a sample, it is only due to common variation or chance variation. And chance and common cause variation is not a problem. It is not a problem. It will not lead to any to a problem to your process. It does not shows that your process is a problem, is having a problem. So if chance causes occurs within individual measurements, between individual measurements within a group, then it will still make your process stable. However, if variation within subgroups, yeah, if there's any variation that you identify to be if there's any large variation, then it must be due to assignable causes, and these assignable causes will lead to a problem to your process. As such, your process will become will not be stable. Okay, so you should be able to differentiate the difference between variation that occurs within a group and variation that occurs between subgroups. Yeah, this is within subgroup. This is between subgroups. So this variation could be due to assignable causes. But any variation that occurs within a group between individual measurement, these are only common or chance cause variation. Okay. So in production application, the rational subgroup represent data collected over a short period of time under essentially identical condition of material, tool, setting, environment, condition, etc. So it means that if you were to select a sample at a point of time, yeah, say for example at one point of time, at time 1 you select 5 observations, yeah, as your sample at time 1. So those observations, you are assuming that for that short period of time for which you select the sample observation, those observations are essentially under identical condition of material, tools, setting, and environmental condition. This is what we talk about homogeneous just now. Yeah, so you're not worried. Yeah, you are not actually worried if there's any variation occurs within one subgroup. Yeah, if there's any variation occurs between individual observations belong to one sample, it's not a problem. Yeah, because they are actually operating being produced under the identical condition. Okay, within that short period of time. Yeah, so remember, if you were to select a group of observation for a sample, it has to be done in sequence. Yeah, it has to be done in sequence. So there are two general approaches for constructing rational subgroup. The first one, sample consists of units produced at the same time, exactly consecutive units. Yeah. Again, as I mentioned just now, it is consecutive units being produced. The primary purpose is to detect process shift. Yeah? So this is one approach. The other approach is sample consists of units that are representative of all units produced since last sample. Yeah. So in this example, for example, you have a batch of items being produced at a point of time. Yeah, you come out with say 10 or 20 items being produced in a very short period of time, and you just randomly select 5, for example. Yeah, so that is a situation whereby you do sampling consists of units that are representative of all units. Yeah, and you are collecting them randomly, yeah, after the whole batch being produced at a short period of time. Yeah, so random sample of all process output over sampling interval. Okay, so sampling interval here meaning that just I mentioned just now, are you going to do the sampling every 1 hour, or every half an hour, or every 15 minutes, every 10 minutes, so on and so forth. So that time period is what you call sampling interval. Okay. So this situation of a snapshot approach, a rational subgroup, behavior of the sampling mean. Yeah, this is the part of rational subgroup. Snapshot, where you do it consecutively. Yeah, this is why you do it the random approach to rational subgroup. Yeah. So for a snapshot, you're gonna have exactly at the point of time the same number of sample observations. Yeah, this one you do it over a period of time. Then you do the selection or collection of your of your observation randomly. Okay, but both should give you uh, similar in such a way that they will give you similar mean values in general. Yeah. So to detect changes in the process over time, subgroup should be collected often enough at appropriate times and that they can reflect the potential opportunity for changes. Yeah. So it must be done over time throughout a period of time. Yeah. So often enough so that you will not leave any problem unidentified, yeah, or undetected, and it should be done at the appropriate time so that it will reflect any problem which might occur, which might have occurred. Okay. So again, if you talk about sampling interval, the issue is cost. Yeah, there is no hard and fast rule. You must always know that large sample is not economical. It's desirable but not economical. Yeah, intervals should be close enough to detect changes in process characteristics, as I explained just now. Yeah, stretching out interval between subgroup in the sample can make any process appear to be in statistical control. Meaning to say that if you have too long sampling interval, you might have missed some presence of assignable causes. Yeah, maybe perhaps 1 hour is too long, or again half an hour is still too long. Maybe you need to reduce the sampling interval. Yeah, so it depending on the nature of your production. Subgroup size will determine the effectiveness and efficiency of control chart that uses them. Yeah, so now here we come into a sample size. Yeah, just now we look at sampling interval. The first one we look at a basis of sampling. Yeah, whether we do a systematic or random sampling, so on and so forth. Yeah, in most cases we do systematic random sampling. Then we look at the sampling interval. Yeah, what would be the sampling interval? What would be the sampling frequency? Yeah, so sampling interval will actually determine your sampling frequency. Yeah, what will be the frequency? Yeah, how frequent do you make sampling out of one production shift, for example? Yeah, so for this slide is on sample size. Yeah, so sample size is again the how many observations that you're going to select for your sample at a point of time. So subgroup size will determine the effectiveness and efficiency of control chart. Sample size about 5 is quite common. Yeah, it's found to work well in detecting process shift of 2 standard deviation or larger. To detect smaller shift, meaning that you have to have a smaller sample size. Yeah, so it is better to use small frequent subgroup to detect large process shift. But if your process shift is smaller, it should be a larger and less frequent subgroup. Yeah. So before you decide on whether you're going to use small or large sampling frequency, or longer or a shorter sampling interval, you must understand your process shift. Yeah, does your process normally end up with or normally have a problem of large process shift or smaller process shift? Yeah, so perhaps as a statistician you don't have much information on this. It has to be the engineers. Yeah, they will tell you this information. Yeah, so this is very important diagram. Yeah, as I said, is in most cases we would prefer large sample size. Yeah, you know why? Because if you have larger sample size, yeah, you can detect the probability of you detecting assignable causes is much higher. Yeah, but in this case, it is more on shift, your production shift. Yeah, if your production shift is larger, say for example 1.5, yeah, 1.5, you can afford to have a smaller sample size. Yeah, say for example 5. Yeah, say for example 5. at the at 1.5 shift, 1.5 standard deviation of process shift, you can come out, you can afford to only to have 5 observations in a sample, or a sample size of 5, and you already have a high probability of detecting assignable causes. Yeah. However, if you are dealing with uh, smaller process shift, say for example, one process shift, process shift of only one standard deviation. Yeah, process shift is how does one value vary from one another. Yeah, one correct quality reading different from one another. If there's large variation, meaning there's large shift. Yeah, so you must understand your production. Yeah, so coming back to this, if your process shift is small, say for example one standard deviation, then but only have 5 uh, uh, observation in a sample, the probability will be much lower. Yeah, will be around 0.223 or 24. Yeah, so in cases whereby your process shift is a smaller, you must come up with a larger sample size so that the probability of you to detect any problem will be much higher. Okay, so this is what this diagram is all about. It is about the shift in process, in your process mean. Yeah, if your process mean is larger, you can afford to only have smaller sample size. Yeah, but when cases whereby your process shift is smaller, for example one standard deviation, then you have to opt for a larger number of sample size so that you have better probability of detecting the problem in your process. Okay. So this is an example. Yeah, normally how many sample that you can collect from one production shift. Yeah, this is an example by AS, American Statistical Quality Control. Yeah, for example, if one production shift, you can produce 500 to 800 items or units. You only need to come up with 35 samples per shift. Yeah, so again, if your production can produce up to 500 to 800 units, you only need to sample 35 samples for one production shift. Okay. Okay, right. So you can take a break for now. So this is going to be quite a long lecture, yeah, because we have quite a lot to cover. Yeah, so perhaps we take a break for a while.